And we are going to be talking today about high-performance VNFs with EPA and Sdn Assist. So, first question we've got is, what is EPA? It is Enhanced Platform Awareness. As we're dealing with virtualization, and this applies specifically to virtual machines running in something in a virtualized environment such as OpenStack or VMware VCD. I don't think there's specific things for Amazon Web Services that can be done for enhanced platform awareness. Where it's available, OSM supports it, and it's actually been supported since the beginning. So it is NUMA node placement, CPU pinning, huge pages, and SR-IOV, or other forms of data plane acceleration. So I'm going to be explaining each one of these concepts, and they are enabled via the network function descriptor. So the first thing, what is NUMA? This is called non-uniform memory access, and it has to do with the way the motherboard is built. So memory is typically segregated in banks based upon each CPU. If anybody's done any server configuration before or taken a look at it, oftentimes you'll find that you need to order an equal number of memory cards as is divisible by the number of CPUs. So if you have 4 cores, each with 10 threads or so, 10 CPUs per core. Then if you have 4 cores, you're going to need a multiple of 4 memory chips in your hardware. Because each bank of memory is actually local to a specific CPU. So the memory controllers are physically really close, and access across it has to be remote. So if you have a process running down here on CPU number 1, then its memory, say, may be in this chip that's co-located with CPU number 1. If that process then does a context switch and say CPU number 1 became busy or overloaded, and the kernel, the hypervisor, decided, I'm going to start running this one on CPU number 0 because it's free, then what happens is the memory needs to be accessed through what is called an interconnect bridge. And that means that the access to the memory is going to be slightly slower because it actually has to go across a physical distance to get to that next set of memory. This interconnect, this all basically comes down to physics and things like that. There's certain limitations on the speed of electricity and the speed of light that happens when this interconnect is invoked. But each nanosecond can make a difference in high performance system. So in order to prevent this interconnect from happening, what we would do is we would say, I want to pin this process to CPU number 1. So that way its memory will be local to CPU number 1, and it will never move to another CPU. It'll never have to cross this boundary in order to be able to gain access to its memory. To complicate things a little bit further, a lot of motherboard architectures have the PCI bus or peripheral bus that is also local to CPUs. So you have situations where, say, network cards 0 and 1 are physically closer to CPU 0, and network cards 2 and 3 are physically closer to CPU 1. So then what you might have is you may have a process that's going to be reading specifically from network card 0, and you'll want to pin that one to the CPU that is closest to the network card, so that way it never has to cross this interconnect in order to be able to access the network controller. So a lot of NFVI's VIMs support this CPU pinning and NUMA topology awareness without any need for configuration. So CPU pinning means, okay, here are the CPUs and the cores, and I want to be able to physically pin this VM to this local memory, this CPU, so it doesn't have to cross the interconnect bus. And NUMA topology awareness is what allows open source MANO and OpenStack to be able to communicate that back to us. So in order for us to be able to know, well, this VM needs to go to this CPU, we need to have topology awareness. And all of this is built in to OSM. So the next performance topic is what are called huge pages. And this again has to do with the Linux, this now has to do with the Linux kernel and not so much to do about the physical hardware of your machine. So a Linux kernel maps memory into pages. These pages by default are 4K in size. If we have 64K of RAM, that means we're going to have 16 million pages that the kernel needs to keep track of. So every time we map a page to a physical RAM address, we have to have this translation look-aside buffer to be able to find where the page is in memory. So this is how we keep track of virtual memory, which includes swap versus physical memory. So there is a translation buffer inside of the Linux kernel that says, okay, I can have 128 gig of virtual memory, 64 of which is physical. So I only have 64 gig of physical memory, but I'm going to allow processes to use more memory than what I have because I'm going to be able to swap some that's not recently used out to my swap file. And this is the technology that's used to say, okay, where does this page actually exist? So now if I have 10K of data, that's going to need to split across 3 pages. And those 3 pages could physically be anywhere in the system. One of those pages could even be on disk. And if I need to access it, the kernel is going to need to say, well, it's not here. I need to pick somebody else's page to write to disk, and then I need to pull this page into memory. So the TLB is a subset of all of these virtual pages, and if it's not in the TLB, then it's going to have to go through a full scan of all of its virtual addresses and figure out where things are. So the more of these memory pages we have, and the bigger the memory we have, the slower all of this is going to get. So what do we recommend once we start getting into larger systems with larger memory and processes that use memory in virtual machines that need to use memory more efficiently because they consume lots of memory? And that is, we recommend the use of huge pages. What that'll do is it'll change the page size from 4K to something larger. Now, unfortunately, the trade-off on that is it can result in memory waste. You can see my 10K of data is using one page, but that page is wasted because there's a lot of extra blank data in there that's not being used. One moment. Just need to mute somebody. Thank you. So there is a trade-off that needs to be decided here. What do we do in terms of a balance between having too many pages and having too much wasted space? Once that's decided, we can go ahead and enable the huge pages. So it allows VNFs to request RAM from a special pool where page sizes are bigger, which allows us to enable better performance. So we don't have to do it for the entire hypervisor. We can do it on bits by bits. We can say, okay, let's leave 24 gigabytes of our RAM as regular pages, and 48 gig of them are going to become huge pages. So this is a tuning parameter that needs to be done at the hypervisor level, but once it's done, the VMs can take advantage of it. So we then, once it's available, we allow a VNF to say, hey, I need to use huge pages because I am dealing with massive amounts of data, large amount of memory, and I need to have very fast access to that. SRIOV is another place where we're looking at getting the every nanosecond of performance out of our network infrastructure. So moving away from memory and the page mapping and the CPUs, we're now talking about the network path. So what happens is there needs to be a map of what VM generated what traffic. So if you were looking back to the firewall, where I said, oh, we've only got one point of egress on the internet, the exact same thing happens inside of a computer. When you have multiple virtual machines, something needs to know, oh, VM number 1 generated this request, and out it goes through the one physical network card. And when the response comes back, somebody needs to figure out, oh, that request was from VM number 1, therefore I need to send that back to VM number 1. So this translation needs to happen at the hypervisor. And this is being taken care of transparently for you all the time by the hypervisor. Now, what SRIOV, or single root IO virtualization, does is it is a technology that's built into your network card. And it works in conjunction with your BIOS to present the one physical network card as multiple virtual network cards inside of your server. So then we can say, okay, VM number 1, you're going to attach directly, as far as the hypervisor is concerned. It thinks it's got, 10 virtual network cards, and it's going to say, VM, you're going to attach directly to this network card. VM2, you're going to attach to another network card. And all of that translation and mapping that we needed to do before happens in the CPU of the network card. And this is significantly faster because the network card is fine-tuned to be able to do that. So SRIOV is a technology that is enabled by the network card, and it offloads this map directly to the network card and doesn't require any CPU power on the hypervisor, doesn't require any memory tables in the hypervisor to maintain it. This can result in a fairly significant amount of network performance improvement depending upon the type of traffic you're doing. So it allows network functions to have direct access to a virtualized version of the network interface card. One moment. It allows the VNF to have direct access to the network card and gives it better throughput. So as you can see here, depending upon the message size, you can get better and better performance when using SRIOV. And it is available in Amazon, it's available in OpenStack, it's available in VMware VCD, etc. So this technology is available in a number of different places. So EPA in general and OSM. OSM does support this in the descriptors. What OSM will not do is it will not change the OpenStack server configuration. Because OSM is an orchestrator of the the virtual machines, the life cycle of the virtual machines only. It's not something that's going to go in and start reconfiguring your servers for you. That is not its intent. SRIOV has to be enabled by somebody on the compute node. Same thing with huge pages. So the OpenStack configuration needs to be done and needs to be given to OSM. You, as the author of the descriptor, need to know this NUMA topology that you're deploying on. OSM will not be able to discover anything about the number of NUMA nodes, the number of CPU cores, the threads per core, the topology of the PCI bus. So OSM is not going to be able to tell you, oh, NIC number 1 is physically attached to CPU number 1. These are things that you're going to need to know in advance before launching the service. So in the case of SRIOV, or in the case of network virtualization, somebody needs to maintain that table map, the translation table, as you said, between which VM generated a packet and the real packet that went out. So in this case, the hypervisor has to maintain that. And this is what we refer to as network virtualization. And there are different technologies that can be used to enable this. One is we're going to emulate the BIOS, and that is very slow, but essentially what it does is it intercepts the hardware interrupts of the VM and maintains that map and generates it out and then returns it back to the VM as a hardware interrupt. The other is what's called paravirtualization, which is the VirtIO driver that you may have seen referred to in previous sessions when we talk about the network interface that's going to be used. And the VirtIO, or paravirtualization, is a piece of software that was written for the Linux kernel, or a driver for Windows that essentially knows it's running in a hypervisor, and rather than trying to talk to hardware, it uses a special memory bus to talk to the hypervisor and says, okay, rather than me pretending to generate a hardware interrupt and you intercepting that interrupt and performing the action on my behalf, here's the data I want to send on the network. But that translation is still all happening in software in the hypervisor. So with SRIOV, all that translation is offloaded from your hypervisor into the network card. So that's a type of hardware offload that because the compute chips, basically the CPUs inside of network cards, are very dedicated to one purpose and one purpose only, it reduces the latency of that lookup because that's all that it does. It's very finely tuned. So SRIOV is very fast compared to us trying to do that in the hypervisor. So all of this information about enhanced placement awareness is not something that's going to be automatically discovered by OSM. These are things that you're going to need to know. And it essentially breaks some of the rules of virtualization. See, because you're now hard coding or encoding in the descriptor, oh, well, you're going to use this network card and you're going to use this specific CPU number. OSM is not going to be able to, just say, hey, this can go on any virtual hypervisor. It needs to be targeted towards a specific one. And if there's a mismatch between what the physical hardware is and what we're requesting, OpenStack is going to come back and say, sorry, I can't comply with this request. And OSM is at the mercy of OpenStack at that point, and it's just going to turn around and say back to you, sorry, OpenStack returned no available hosts found. I cannot launch this network service. So there is nothing magic that OSM can do when it comes to finding the right hardware for NUMA or SRIOV. It must be known in advance. So that's one of the considerations. The next thing we're going to talk about now is Sdn Assist. And this is where the Sdn controllers get their well, basically, it's a type of offloading or a type of processing for network switches that allow us to enable virtualization much more easily. Traditionally, inside of a switch, the control function and the forwarding functions were both part of the switch. Now, what does that mean? It means that the switch needs to maintain a map of, oh, IP address .57 is over here, and it's going to be associated with a MAC address, and I need to route it through this next point. So there's this big map of where packets need to go, and it needs to compile this and send it to the next layer down, which is the forwarding function. You see, in order to achieve great performance on switches, they don't want to take a look for every packet coming in, where's it supposed to go next. They want to pre-compile all of those routes and make sure that it gets to the right place. So that's all predetermined ahead of time, and that's put right down at the lowest layer. And what an Sdn controller does is it removes all of this control function from the lookup of the packets and creates essentially a virtual overlay map to exist on top of the physical network. So what we see is a logical view of the network, and the switches underneath already have the rules that we want in them pre-set up, and they don't have to do any lookups at packet forward time. Taking a look at the time, we have placement coming up. I'm actually, I believe right now, eating into the placement time. So I will be available in Slack to talk about Vim technologies and EPA afterwards. So I'm just going to finish up on the Sdn Assist now. So OSM is currently supports a number of different vendors' version of Sdn controllers. We have plugins for Arista, Floodlight, Juniper, Open Daylight, and Onos. So the way this works is that you have data that's coming from, say this VM, and then inside of the hypervisor is a virtual switch, which presents a real switch, which then needs to traverse the network topology to be able to figure out, okay, this packet from VM2 needs to go from switch 1 through to switch 99, through to switch 3, and get to VM4. And all of these different lookup points and decisions about where the path goes costs a tiny bit in performance, and it's brittle. It's something that you need to make sure that you have your IT department involved in, and if configuration changes are needed, we need to be able to involve them. So the way these things are typically done is we create a VXLAN, which is a software, it's basically an extension that's put on every single packet to encapsulate the packet that we're sending between VM2 and VM4 that are passed back and forth through the network. So switches like OVS, which can run inside of your hypervisor, they typically have limited performance because these are all software things. Now, you can use some network virtual acceleration technologies. DPDK is one of them to help speed this up, but DPDK comes at a cost. And that DPDK cost is that it requires you to dedicate one entire CPU thread to doing nothing more than constantly polling the real network interface to see if there's data ready to send or ready to be received. So these physical interfaces are only used to tunnel the actual traffic. So inside the vSwitch, each packet going out gets wrapped up in a VXLAN header and then sent over the real switch to be able to go to the next hop. The next virtual switch will see that packet coming in, unwrap it, and send it to the VM. So this again is a type of data table lookup that we need to do. You can do this using SRIOV pass-through. So we can go ahead and basically pin directly to the real physical switch and have all the real physical switches do the networking and maps back and forth. But then we've lost our virtualization aspects of the network. Now the IT department must physically cable everything. We must configure each switch so that the IP addresses are known, the IP routing tables are all there, and everything. The other unfortunate thing is any one tenant could technically see traffic that belongs to another tenant because this is all one flat network now. And it's, switches inside slide 11, Sdn compatible. We'll get to that in just a moment. Yeah, so basically this becomes a flat network. It becomes a very physical network. And moving things around or adding new nodes to this environment requires configuration of the switches to make it work. So there is nothing in this type of environment, although it's faster performance, there's nothing that enables us to be able to create new networks on demand and isolate them from each other. So what Sdn Assist does is OSM orchestrates the pass-through, and it gives the ability to create layer 2 connections between different virtual functions. So this is a little bit, sort of detailed. There's a lot going on here at once, but I'll try and break it down. The SDN, so we'll go through the top layer. OpenStack, the open source MANO says to OpenStack, please create me 2 VMs on 2 different compute nodes with physical, I should say, virtual functions, network functions that are attached to a physical switch, NIC. So we're getting SRO capabilities here, but contrary to this previous picture here, while the real packets are going out on what looks like a physical switch, on the other side, RO is also communicating with the SDN controller and says, oh, hey, you are a smart switch. When you see this data coming in, please encapsulate it inside of a flow that will route it and keep it like VXLAN, keep it in a virtual network between these 2 nodes and these 2 nodes only. And that way it's hidden from any of the other VMs. And from the compute node perspective, it thinks it's talking pure hardware. Performance is as best as it can be up here. And on the physical switch side, it is also offloading everything in hardware, and it's taking care of all of these translations in hardware, freeing up the CPUs on the compute node from doing all of this, because we're not running virtual switches in here, we're running physical switches out network. And these physical switches are smart enough that OSM can tell the SDN controller, here is the data flow that I want you to have between 2 systems. So these switches here have to be SDN capable, because there's going to be an SDN controller such as Juniper or Onos or something like that that is controlling the switches. OSM does not talk to the switches directly. OSM will talk to the SDN controller. So that now looks like this, where the SDN configuration, SDN controller basically, is programming the switches, and we're able to use physical offload or hardware offload on all of these servers. Like EPA, OSM doesn't actually manage your SDN controller. You have to have an SDN controller installed, just like you have to have OSM installed. So the SDN controller must be installed. You must have it reachable from OSM. So you're going to need to have credentials and such in order to be able to talk to the SDN controller. OSM uses what interface to talk to the SDN controller? Depending upon where you installed OSM, you're going to be talking to the SDN controller using TCP/IP, which eventually, through a host name, will translate to an IP address, and it will use the IP routing table of the server that you installed OSM on to talk to the SDN controller. So some of the plugins are more involved than others. Some of the plugins will require additional information. Other plugins may be much simpler. And of course, the Vim account must have admin privileges. So there are certain things that are required in order to be able to enable Sdn Assist. In our example, there's not all that much here that we could enable SRIOV for, but we could have enabled it right here between the virtual desktop and the Apache web server. So when the virtual desktop attaches to the private network, it could have attached to it using an SRIOV capability, and that would have given us a little bit more performance talking to our web server and talking out to our firewall. Wasn't really, we're not doing, say, cellular control plane data processing here. We're not passing huge amounts of data back and forth, so it didn't really make all that much sense to do this. So with that, I have wrapped up this session.